All right, let's talk about absolute value. You know, those two little vertical bars we all learned about in math class? It seems so simple, right? Whatever number is inside, just make it positive. Easy. But here's the thing. That simple rule is actually a trap, one that trips up almost everyone, from students all the way to their teachers.
So why is it so tricky? I mean, how can something that feels like basic arithmetic cause so much confusion? Well, it turns out the real power and the real trickiness of absolute value has almost nothing to do with just dropping a negative sign. And hey, if you've ever been stumped by it, you are in very, very good company.
And I'm not just saying that. A study from 2024 looked at people training to be math teachers, the pros, and found that most of them actually struggled with it. This isn't just a student thing. It's a fundamental misunderstanding that's way more common than you'd think. So today, we're going to bust the 3 biggest myths that make absolute value so confusing.
Okay, let's kick things off with myth number 1. This is the big one, the idea that the absolute value bars are just some kind of make-it-positive machine. This is what we all remember, right? And look, it's not technically wrong, but it's dangerously incomplete. It tells you what happens, but it completely leaves out the why. And that why is the key that unlocks everything else. And that's the trap right there. Thinking of it as just an action you take. There's a much more powerful and frankly more useful way to see it. Think of absolute value as distance. This one change in perspective makes all the difference. The absolute value of -4 is 4, not because we just erased the minus sign, but because -4 is exactly 4 units away from 0 on a number line. And guess what? +4 is also 4 units away from 0, and since distance can't be negative, this one simple idea, distance from 0, is the real foundation here. This whole distance concept is what gives us the official, formal math definition. Now, it might look a little intimidating, but it's actually simple. It just says, if the number inside the bars is already positive or 0, don't touch it. But if the number inside is negative, you multiply it by -1 to get its positive distance. So for -4, you do -4, which gives you +4. Same answer, but a much more solid logic behind it. All right, on to the next myth. This is what happens when we start solving equations. It's a classic mistake. Our brains see those bars and immediately think parentheses. Research shows this is one of the most common ways people get these problems wrong because it makes them miss half the answer. Just look at this. On the left, that's the trap in action. You treat it like parentheses, you solve for x, you get 8, and you move on, thinking you're done. But if we remember our distance definition, we're asking a different question. What numbers are 6 units times away from 2? Well, 8 is 6 units away, but so is -4. This is why you have to check both cases. The stuff inside could equal 6, or it could equal -6. That's how you find both answers. And if you're a visual person, a graph makes this crystal clear. An absolute value equation creates this classic V shape. Solving it just means finding where that V crosses the horizontal line at y equals 6. And what do you see? It hits the line in 2 spots, plain as day. One at x equals -4, and the other at x equals 8. The graph doesn't lie. Speaking of that V shape, that brings us perfectly to our third and final myth, the idea that all absolute value graphs look exactly the same. Sure, the basic one is a perfect V, but that's just the starting point. Yeah, think of y equals x as the default setting. Just like with other functions in algebra, we can totally customize it. We can stretch it to make it skinnier, shrink it to make it wider, flip it completely upside down, and move it all over the graph. It all comes down to this one formula, and it's not as scary as it looks, I promise. Each letter has a simple job. The A out front is the shape controller. It handles the stretching, shrinking, and flipping. The H and K are the location controllers. H moves the V left or right, and K moves it up or down. That's it. And you can see it right here. If you multiply by a big number, you get a much narrower V. If you add or subtract inside or outside the bars, you just pick the whole shape up and plop it down in a new spot. So graphing any of them is actually a really simple 3-step process. First, find your home base, the vertex, which is just the point HK. Put a dot there. Second, use the A value as the slope to draw the right side of the V. And third, use the opposite of A, or -A, as the slope for the left side. And boom, you're done. You can graph any of them. And this brings us full circle. This is why understanding the graph is so powerful. When you need to solve an equation like this one, it's really just asking, where does my shifted v shape cross the line y equals 7? And again, you can literally see the two solutions. Okay, so we've busted the 3 biggest myths, but I've saved the most interesting, most mind-bending part for last. This is where we see that absolute value isn't just some random rule made up for math class. It's actually baked into the very fabric of how numbers work.
So let me ask you a question that sounds almost too easy. What is the square root of x squared? Now, your gut instinct, and pretty much everyone else's, is to just say x, right? The square root and the square should just cancel each other out. But that's not the whole story. Let's try it with actual numbers. The square root of 3 squared is the square root of 9, which is 3. Okay, no surprise there. But now look at the right. The square root of -3 squared, well, -3 squared is positive 9. And the square root of 9 is 3, not -3. Why? Because the square root symbol, by definition, always gives you the principal or non-negative root. And there it is. That's the big reveal. The square root of x squared isn't actually x. It's the absolute value of x. This is the hidden connection. It's the rule that guarantees the answer is always non-negative, which is exactly what our distance definition demanded all along. What this all means is that those two little bars are way more than just a piece of notation. They represent a deep, fundamental property of numbers that just naturally pops up when you do other things, like take a square root. It's a core feature of math, not just a procedure to memorize. And that kind of leaves us with one last thought. If a concept as simple as absolute value is hiding this much depth and has this cool secret identity, it really makes you wonder, what other easy math rules did we learn that are just the tip of a much deeper, much more interesting iceberg?